It was Shakespeare that first wrote, "All that lives must die." And it was Turritopsis dohrnii, the immortal jellyfish, that responded, "No, I don't think I will." Death isn't just a certainty for most life forms, it's a necessity. It contributes to ecosystems, controls populations, and drives natural selection. So, why would the immortal jellyfish, and several other organisms for that matter, have evolved the capacity to live forever? Today, I'm going to go over the 4 different types of immortality found in nature, how they work, and how they can inform us about anti-aging treatments in humans. Just how far away are we from living forever? Well, don't die before this video ends, and maybe you'll find out. Let's start by making the distinction between chronological age and senescence, the deterioration of an organism that happens over time, sometimes referred to as biological age. When people talk about anti-aging treatments, they really mean anti-senescence treatments. In fact, the goal is precisely to age without senescing. And it turns out plenty of animals can do just that. Negligible senescence is the first and most common type of immortality that we'll be discussing. Rather, it's a method to hypothetically achieve immortality. Greenland sharks have the longest lifespan of any known vertebrate, from 250 to 500 years. In comparison, the oldest tortoise in the world is currently 192 years old. His name is Jonathan, by the way. I just thought you should know that. But yeah, Greenland sharks can get very old. They reach sexual maturity at 150 years old. When they're pregnant, their gestation period can take anywhere between 8 and 18 years. And they, on average, grow to be bigger than great white sharks, because why not? Researchers took enzymes from sharks from 60 to 200 years old and used them to measure their metabolic activity. In most animals, this would be expected to decline substantially with age. But they found that Greenland shark metabolisms don't show any change at all. This appears to be the secret to their longevity, a metabolic system that never appears to decline with old age. In humans, metabolic activity steadily declines with age. Though there is evidence that this can be prevented through diet, resistance training, and certain therapies. Seeing as how these things also correlate with longevity, maintaining an active metabolism may be a core mechanism that allows us to slow down senescence. But this is something that we can learn a lot more about by studying Greenland sharks. Research on them is both slow and difficult, as they're a vulnerable species that has a low population density to begin with. Very Greenland of them. This is the hydra, a genus of freshwater animals that share ancestry with jellyfish. Despite their size, they are ruthless predators, using their tentacles to sting and release neurotoxins that paralyze their prey. Hydras have been popularly cited as animals that can be considered biologically immortal, as their cells are capable of infinite self-renewal. We'll get into why our cells aren't capable of this in a bit, but for now, just know that this is a remarkable thing to do. Even better than the Lernaean hydra of Greek myth, the real-life counterpart can fully regenerate its body from only a small fragment. Scientists have identified the transcription factor FOXO as the driving force for the hydra's infinite rejuvenation. They did this by experimentally removing several genes and factors and seeing what would happen. And when FOXO was downregulated, hydras appeared to die more often and reproduce less frequently. It turns out all other animals have FOXO genes. Invertebrates have one copy of the FOXO gene, and when downregulating this, we find that their lifespan significantly decreases. In vertebrates, this gets a little more complicated because we have 4 FOXO genes, FOXO 1, 3, 4, and 6. Don't ask me what happened to 2 and 5, I don't know. We know that these genes have downstream effects on human longevity, but they also do a whole bunch of other things as well. So the goal is to disentangle these effects to get a better idea of how FOXO impacts human lifespan. There's a lot of exciting research on that right now, and we have the hydra to thank for that. Some other animals that show negligible senescence are Olm salamanders, Aldabra giant tortoises, which is what Jonathan is, red sea urchins, rough-eye rockfish, freshwater pearl mussels, and ocean quahog clams. Of course, lots of trees are like this as well. The oldest tree in the world, which has been standing for almost 5,000 years, is the bristlecone pine Methuselah, named after the biblical guy who supposedly lived for 969 years. Though we've been given a lot of hints about aging by studying animals, the exact mechanisms that cause senescence in humans are still a mystery. There are literally hundreds of theories ranging from DNA damage to the accumulation of mutations, to our immune systems being pre-programmed to shut down. But none of them seem to be entirely satisfactory on their own. There are just so many different factors that contribute to age, some of them unknown and some of them we don't have time to get into. But there is one that absolutely needs to be highlighted, and it has to do with these things called telomeres.